Hey guys, in this lecture we are going to look at the hydroxylation reactions of alkene, and then this will be lecture 4 of our oxidation lecture series. Now let us look at the objective of this lecture. Now at the end of this lecture you should be able to determine the oxidizing agent used and the product of dihydroxylations of olefins. The olefins are also called alkene. Now in the previous lecture we talked about various other methods of adding oxygens to alkene. We said that the addition of oxygen to alkene is called the oxidation reaction. So at the end of this lecture you should be able to determine the oxidizing agent that is used and the products of the hydroxylations of olefins. Now the question is, what is dihydroxylation? Now from what you can see here, di means 2, then hydroxylation means addition of OH group. So we can say that dihydroxylation, I think we should go with the word di. Dihydroxylation means the addition of 2 OH group to the alkene double bond. So whenever 2 OHs are added to the alkene double bond, you say such a reaction is called a dihydroxylation reaction. Now, dihydroxylation of alkene is one way to introduce alkene or to introduce oxygen into the double bond of alkenes. The product of dihydroxylation of alkene is usually a glycol, or you can say a diol. Diol means a group of compound, or let's say a compound that has 2 OH group, because the OH group is called the or functional group, which is for alcohol. So diol means 2 of the OH group, right? Now the glycol is a compound, saturated compound. It's a saturated compound that has 2 OH groups on adjacent carbons. For instance, let's say this is a carbon, this is a carbon. Now if you have OH here and then you have OH here, this kind of compound is what is called a glycol. So this is a glycol, right? This is a glycol. So the product of the hydroxylation of alkene is a glycol. Now to dehydroxylate alkene, we ought to dihydroxylate alkene. Let me use the word di, not d. D is different. D means to remove, right? Dihydroxylate. Like I said, to dihydroxylate alkene means to add 2 OH groups to the double bond of alkene. What we mean is, for instance, let's say this is an alkene, C double bond C. This is the general form of all alkenes, right? Now this alkene, if you put the reagent, let's say oxidation reagent, is going to form something like this. C, C, here is OH, here is OH, and then here is hydrogen, or let's not say hydrogen. These are the group that are present there. Now this compound here that has OH on adjacent carbons is what is called a glycol, or you can call it a diol. Diol means it has 2 OH group. Glycol means the 2 OH group are adjacent, or they are present on adjacent carbon atom. Now when you want to dihydroxylate alkenes, what reagents do you think should be used, or what oxidizing reagent is used for the dihydroxylation of alkene? Now 2 reagents are particularly useful for the dihydroxylation reaction, but we are going to make them 3. There's a third kind of reagent, but that is not mostly used, or is not used in most cases. The 2 reagents are 1, osmium tetraoxide. First one is osmium tetraoxide, which is OSO4. And then the second reagent is potassium permanganate. or you can call it KMNO4. Potassium permanganate has been a very good oxidizing agent that we've been looking at since, KMNO4. And then the last one is iodine silver acetate. The iodine silver acetate is also called the Prevost reagent. So if you hear of the word Prevost reagent, or if you hear someone say, get me a Prevost reagent, what they expect you to bring is iodine silver acetate, which is an oxidizing agent that is used for dihydroxylation of olefins. Now, I believe that I've actually talked about something like this in our previous lecture, that the place where olefin reaction occurs is the double bond, because the double bond is the functional group of alkenes. I would say the functional group is the group, or is a group of atoms, or a bond, or an ion that actually determines the chemical reactivity of a compound. So this is the functional group of the alkenes, and that is where the reaction will occur. So you add two OH group and this functional group to form a glycol or a diol using any of these oxidizing reagents: osmium tetraoxide, potassium permanganate or KMNO4, iodine silver acetate, or the Prevost reagent. Now let us look at the osmium tetraoxide dihydroxylation. Now osmium tetraoxide has the formula of osmium tetraoxide is something like this: OSO4. Now if you want to write the Lewis structure, you have this OS in the middle. This is the Lewis structure: double bond oxygen, double bond oxygen, double bond oxygen, double bond oxygen. This is the Lewis structure of osmium tetraoxide. So we can say Lewis structure. Now osmium tetraoxide, also called osmic acid. It's called osmium tetraoxide or osmic acid. Reacts with an alkene to form osmic ester. It reacts with an alkene to form osmic ester. What do we mean by that statement? Something like this. You have now this is an alkene. Let's say this is the structure of an alkene. It's usually in this form. Let me put it here: C, double bond C. There you have this bond to make the valency of carbon complete, plus osmic acid, which is the osmium tetraoxide. Now this will undergo what we call a consacted mechanism. The reaction is consacted mechanism. So you can say mechanism of reaction is consacted. We can come here and say mechanism is consacted. Mechanism. Now when you say a mechanism is consacted, what does that mean? It means that it takes place in just a single step of the reaction. Now when this react with this, what do you think would happen? First of all, this double bond here will come here and then attach, form a bond with this carbon here. This is how the reaction takes place. That's what I'm trying to show to you. Then as this one is coming here, the valency of carbon is more than the required. So what will happen? This bond here will come here and then pack at this point. Now at this point here, this cannot stay here because the valency will be more than. So this one here will come and then pack on this oxygen or osmium. So this will form this as a product of this reaction to form something like this. You have the carbon. Of course, you know this will no longer be a double bond because one of the bond has moved to this place. So you have carbon, we have all this bond here, this one, and then there will be a linkage. If you look at it very well, there will be a linkage between this oxygen and this bond here because this bond here has come to this place. So there will be a linkage here where you have this as the oxygen. Also, this one came here, so there's a linkage here also. So you have a linkage here, and then you have the osmium, which is OS double bond oxygen, double bond, oxygen. So in this reaction, this is what is called the osmic ester. Now, this osmic ester can undergo hydrolysis. So we can come here and say this is hydrolysis with H2O2, which is hydrogen peroxide, or tertiary amine oxide, right? Or tertiary amine oxide. The oxidation hydrolysis is either by hydrogen peroxide H2O2 or by tertiary amine oxide. Now, when you talk about hydrolysis in chemistry generally, what they are trying to tell you is a breakdown of something. Are you getting it? A breakdown of something. So this complex here, let's say this is an intermediate here, this is the osmic ester intermediate, will be broken down, and when it is broken down, the product is the glycol, which is something like this. So the product of this reaction would be this C, here will become OH, here is OH. After acid hydrolysis, then you have this double bond here, plus this osmium tetraoxide will still remain at the end of the reaction. So now, what do you actually know about substances that catalyze, or some substances that help a reaction but is not used up during the end of the reaction? We call them catalysts. Can you remember when we are learning about catalysts, we said catalysts are substances that speed up the rate of a chemical reaction without being used up during the course of the reaction. So can we now say that this osmium tetraoxide, it acts as the oxidizing agent and also what? More like a catalyst in combination with this osmic ester, because at the end of the day, this osmium tetraoxide still remains back at the end of the reaction. This is the product, which is a glycol. Now, this hydroxylation is let me explain it in this way, that when you talk about addition, because alkene generally, let me put that under this place here. Alkene generally undergo what kind of reaction? Alkene generally undergo addition reaction. Is that okay? Yeah. Now, the two types of addition reactions of alkenes are: one, you have what is called the syn addition, and two, you have what is called the anti-addition. Now, what is the syn addition and what is the anti-addition? For instance, let us say you want to add something to this double bond of alkene. Let's say you want to add 2 OH, 2 hydroxyl group, which is dihydroxylation. Now, the syn addition says that when you add it, this double bond normally will break, right? So we have a single bond here. Then this OH will be on one side of the double bond. This kind of addition is what is called the syn addition. When the incoming substituents are added, or the materials that are being added are added to just one side of the alkene, it's called the syn addition. However, a situation where, so we can call this syn addition. However, a situation where you have it in this way, let's say this one is the OH, and then the other one, the OH, is on this side, you call it what? The anti-addition. So osmium tetraoxide dihydroxylation reaction is syn addition, in the sense that the 2 OH group are added at one side of the alkene. The 2 OH group are added at one side of the alkene to form a glycol. So as a way of repetition, let us just analyze what we have. We said that osmium tetraoxide adds to alkene. This is alkene, right? And then this is osmium tetraoxide, which we can also call osmic acid. And when they react, they are going to form an osmic ester, right? Now, this osmic ester will undergo hydrolysis with H2O2, which is hydrogen peroxide, and tertiary amine oxide to form the glycol with the osmic acid again not being used up during the course of the reaction. Are we getting it now? So if they ask you, give and explain the process of hydroxylation or dihydroxylation of alkene using osmium tetraoxide. First of all, the alkene react with the osmic acid to form the osmic ester, right? In a concerted mechanism. So stereochemically, if we talk about the stereochemistry, the product formed will still be the same thing as those of the alkene initially. What we mean is the stereochemistry of the product will be the same as those of the alkene. The reason being that the reaction takes place in a concerted mechanism. Since it takes place in a concerted mechanism, there is no change or an inversion of the stereochemistry or the configuration. Is that understood? What we mean is that if the alkene is a cis alkene, the product here will also be a cis glycol. Let's take it like that. If the alkene is trans alkene, the product here will also be a what? A trans glycol. That is what we mean by that stereochemistry, because it takes place using a concerted mechanism, which is a one-step mechanism. All right, so let us predict some. Say, predict the product of this reaction using osmic acid and hydrogen peroxide react with alkene. Of course, you know this is going to form a glycol, right? So the glycol that will be formed is something like this. I don't need to write the mechanism now. We were just asked to predict. Of course, you know that the double bond here will break, right? So if the double bond here breaks, you have hydrogen, hydrogen. Then you have the OH, right? Let me use a different pen. The OH that indicates what is being added, right? So this is the product of this reaction. Now, same thing applicable here. There's supposed to be a double bond here, because you're talking about alkene. Supposed to be a double bond here, right? Now, in this case, what do you think will be the product of this reaction? It's still very much easy. First of all, let us draw this structure, which is something like this, something like this, something like this, like this, something like this, something like this. Then you have this coming here, right? Now, at this point in time, this double bond will break, and then you have the 2OH group attached to this part. So you have, let's say this is OH, hydrogen, this will be OH and what? Hydrogen. So this is the product of this reaction, depending on the stereochemistry of the initial alkene. Now this is a bicyclo compound. At this point in time, we should be working with bicyclo compound and not just cyclic or straight chain compound. That is why in most of this lecture I'm introducing bicyclic compound. All right, so that is the product of this reaction. Now what you are going to do for me now is predict the product of the reaction below, this particular reaction. What do you think is the product? Very easy. You have some time to work on it yourself, but I'm going to also provide the solution to it. What do you think is the product of this reaction? It's very easy. You just add the OH here, and then we can rearrange it to form something like this. Hydrogen, this CH2, CH3. Coming here, this is carbon, hydrogen. Here is CH2, CH3. And then you have this OH here, and then this OH here. Now, if I want to rearrange this, I can rearrange this to give me something like this. Carbon, carbon. Now, this CH3, you know, it's still on top of this carbon, so I can decide to bring it up here. CH2, CH3 rather. Then we have our OH, and then you have your hydrogen, spreading it across the 4 valency of carbon. So same thing applicable here. You have your OH here, you have your hydrogen, and then this with CH2, CH3. Now, what kind of compound is this? This is a meso compound. Can you still remember meso compound when we talk about stereochemistry in year 2? Meso compounds. Now, what are meso compounds? Meso compounds are non-super They are non-superimposable mirror images. Sorry, they are mirror images of each other, but they are superimposable. For instance, look at this one. If you divide this into two, this side and this side, they are what? Almost the same. Are you getting it? If you cut it into two like this, they are the same. So they are superimposable mirror images of each other. So this is a meso compound. Compound that can be divided into two equal parts. Meso. Alright. So that is that on this osmium tetraoxide dihydroxylation. So as a way of recapping, osmium tetraoxide dihydroxylation is a kind of dihydroxylation of alkene whereby the osmic acid, the oxidizing agent, reacts with the alkene to form the osmic ester. The osmic ester now will undergo hydrolysis in the presence of hydrogen peroxide and tertiary amine oxide to form the glycol, with the osmic acid being formed at the end of the reaction. And we say that that process uses what is called the syn addition. Syn addition means that the OH are added at the same side of the double bond of alkene. Now the next one we are going to look at is permanganate dihydroxylation. Now potassium permanganate can also be used in this process. Potassium permanganate is KMnO4, right? We said that it is a very strong oxidizing agent. However, this potassium permanganate that you are using here, it's cold one, not the hot one. So we say cold potassium permanganate, and it should not be that concentrated. Now, I'm going to tell you the reason why it should be cold and not that concentrated later. Reason being that if it is hot, it's going to cleave this cyclic structure and it's going to form an opal chain compound. Are you getting it now? So a cold, not too concentrated KMnO4 will cause dehydroxylation. Now what we do here, the process is still the same thing as those of osmic acid, but this K here cannot work with this, so K will leave, and then this is going to form MnO4 minus. Now if you write the Lewis dot structure of this, it's something like this: Mn, then you have double bond oxygen, double bond oxygen, double bond oxygen, and then you have O minus. Now this O minus is where this potassium normally attached here, K plus and minus, they will cancel out to give us a neutral compound. So this is the Lewis structure of potassium permanganate. Lewis structure, right? So when this react with this compound, what do you think is going to form? It's still the same process as the one that we've discussed before. Potassium permanganate now react with this, react with alkene. Like I said that like osmium tetraoxide, these ones still react the same way. So we have manganese permanganate ion, which is something like this: Mn, then we have double bond oxygen, double bond oxygen, then we have this as O minus, or let's say the double bond oxygen, then here should be the minus. Now when these react, what do you think is going to form? It's very easy. The same way that the other one reacted is the same way it's going to react too, right? Now how did the other one react the other time? We said this oxygen here actually form a bridge. This oxygen here came here, right? As it's coming here, this one will leave to this place. As this one is leaving to this place, this one will pack on top of this, right? And then the product will be osmic ester. So now this product will not be osmic ester anymore, but it's now going to give us the manganate ester instead of osmic ester. So the manganate ester will be something like this. This will be the structure of the manganate ester. It's quite an easy one, but at the same time quite complicated. So we have the oxygen, and then here you have the manganese, Mn, this one oxygen here in the middle, and then of course you have O minus. This thing is not allowing me to write here, and then you have this oxygen here, right? So this is the manganate ester that will be formed. So in place of osmic tetraoxide, you form osmic ester. Why this? You form magnate ester. Now this magnate ester that is formed will undergo reaction with a base O minus, OH minus, right? When it undergoes that reaction with the magnate ester, will undergo reaction with, or will undergo hydrolysis with a base, right? Now, if it undergoes hydrolysis with a base, the product will be the glycol, which is something like this. It's going to give us something like this. Then we have OH, and then we have OH, right? Glycol plus Mn manganese dioxide, right? Now, in addition to the synthetic value of this, that means in addition to the synthesis of glycol using KMnO4 as the oxidizing agent. Now, this is also one of the chemical tests for alkene. It's one of the chemical tests for alkene. Now, alkene discolorizes the purple color of KMnO4. So, if you have, let's say this is an alkene plus KMnO4. KMnO4 is purple. Do I have a purple? Is purple, right? Deep purple color. That is what KMnO4 is, the color of KMnO4. It has a deep purple color. Now, at the end of the day, if it reacts with alkene, it's going to form a rusty brown, something brownish precipitate, or it gives that opaque, murky brown color of manganese dioxide or manganese dioxide, which is this one at the end of the reaction. So at the end of the reaction, you form this, right? Now this color is somehow brownish. Is there any brown color here? No. Let's use this rose blood, but it's not that. This is not that brown, right? So it forms that kind of a brown color of manganese oxide. So this is one of the chemical tests. Now, it is not only alkene that decolorizes KMnO4 to form this brownish thing, but most compounds do not decolorize alkene. I mean, this does not discolorize KMnO4 as much as alkene we do that. Is that understood? So, in addition to its synthetic values, that means in addition to this KMnO4 being used for the synthesis of glycol, it is also a good test for determining the presence of alkene in a particular compound. All right, because alkene decolorizes the KMnO4 color from this clear purple color to a brownish, not too clear, that means opaque coloration. Is that understood? So now let us look at the next one, iodine silver acetate, the Prevost reagent. Now, iodine silver acetate, which is also called Prevost reagent, reacts with alkene under wet condition. Now, under wet condition, is going to form a cis product, while it gives a trans product on dry condition. So, under this wet condition, it's going to form the cis product. Cis product in the sense that the two OH group will be on the same side. So, the product of this reaction will be something like this: OH, and here we'll have hydrogen C, here is OH, and here is hydrogen. Now, this one is going to give us a trans product to be oxidized. Now, this one is going to give us a trans product. Now, of course, you know the valency of carbon is not complete here, so we have to add one hydrogen here to complete the valency, hydrogen. So if we want to rearrange this, we can decide to do it like this. to make it more beautiful. This is hydrogen, 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 and then OH, and then hydrogen, right? This is the cis product. Now under wet condition, the product that is formed is the trans product, which is something like this. So here you form the OH, and then here you form the OH. There you have this hydrogen. Sorry, there will be no OH here. This will be hydrogen. So that is the reaction for the iodine silver acetate, which is also called the Prevost reagent. Iodine silver acetate. After hydrolysis, we give these two products. So that is one way of dihydrosylating alkene. Are you getting it now? So we've talked about how many ways of dihydrosylating alkene. We talked about 3 ways of dihydrosylating or dihydrosylating alkene. The 3 ways are osmic acid, addition of osmic acid, which is osmium tetraoxide. Then we have KMnO4, then iodine silver acetate. Is that okay? Now we say KMnO4 and osmium tetraoxide, they work hand to hand together. Now, if you have a choice between osmium tetraoxide and KMnO4, which of them do you think is better for oxidation process? Now, in most cases, it is better to use KMnO4 than osmium tetraoxide. Why? Because osmium tetraoxide is very dangerous to use, right? It's very dangerous to use, and it is more expensive than KMnO4, but it gives more yield as compared to KMnO4. So that is everything you need to know about this dihydroxylation reaction. Now in our next class, we are going to look at epoxidation reaction. I think that should be in the next class. Yeah, lecture 5 will be epoxidation reactions of alkenes. Thank you very much for your time.